Hey, thanks so much for being here. Good afternoon. My name is Will Benton, and today I'm going to spend the next just under half an hour telling you how to get started building machine learning algorithms on Apache Spark. So this talk is going to have a mixture of high-level concepts and principles and some code. So I want to get a sense for where people are coming from. How many people here consider themselves primarily data scientists? Okay, good. How many people consider themselves primarily developers? How many people are a little bit of both? Great. And for people who spend time writing code, how many people use Python as their primary language? Java? Scala? Okay, so I've tried to be as neutral as possible in my code examples, so everyone will have something to be slightly disappointed about. Scala programmers won't prefer the slides with Python examples. Python programmers won't prefer the slides with Scala examples, and Java programmers might not prefer the slides that have code examples. Where I've used a particular language feature that isn't in all the languages, I'll try and explain it though. So there are a few reasons why you might want to implement your own machine learning algorithms on top of Spark. Maybe MLlib or a Spark package offers something that's really close to what you need, but it doesn't totally fit your requirements. You might need a different distance metric, for example, and it's easier to just sort of implement a customized version. Maybe you recently wrote a paper and you're inspired to try out a new technique, but there's no implementation you can use yet, so you need to start from scratch. Or maybe you have a technique that you like using in another library, like an R package or in scikit-learn, and you can easily integrate these kinds of things with Spark and some glue code. But that really doesn't help you benefit from the generality of Spark, right? One of the cool things about Spark is that you can use Spark for everything. So you might want tighter integration with the rest of the ecosystem and run as a scale-out implementation on Spark. So I developed an implementation of self-organizing maps for Spark's RDD API early last year. And I ran into a few snags with the initial implementation, but things really got more interesting when I decided I wanted to make it easy for other people to use the code, which meant targeting modern APIs like data frames and machine learning pipelines. So the rest of this talk is a story of what I learned along the way, but we'll start with a quick overview of the self-organizing map technique to provide a little bit of context. We'll discuss some of the challenges involved in taking a serial technique from a paper and translating it to a parallel technique, paying particular attention to the details of implementing those on top of RDDs. We'll then look at what we need to do to extend our basic parallel implementation by supporting data frames and machine learning pipelines, and we'll close with some suggestions to keep in mind as you develop your own techniques. So self-organizing maps are an unsupervised technique for producing a low-dimensional and discrete representation of a feature space. The basic idea is that you learn a representation so that things that are similar in the feature space are close together in the representation. So this is the technique that's useful for visualization and dimensionality reduction and has some things in common with clustering. I think the best way to get an intuition for what happens in self-organizing map training is to see the training process in action. So I'll just show you what a map looks like over the iterations as you train it. We're starting with a random map, and we're training it with color data using angular similarity in the RGB space to identify similar colors. As training progresses, each example is going to affect a smaller part of the map until eventually the effect of any individual example we see is going to be extremely localized. And we can see this progress as this map goes from random to washed out and desaturated to having identifiable areas of color in different places, and thanks to the projector, getting kind of psychedelic and horrifying. In the classic online training algorithm for self-organizing maps, we start with a map that's initialized to some values. In this case, we're using a random map, but it doesn't have to be random. And then we then repeatedly consider the examples in our training set. When we see an example, we identify the entry in the map closest to it, which we call the best matching unit. We then update the map to bring the area around the best matching unit closer to the example. We do this so that the best matching unit is affected the most, and so that units further away are affected less and less. This technique is pretty powerful, and you can fit an implementation of it on a slide. By processing the training set in random order every time we pass through it, we prevent the accidental organization of our training data from biasing our map. There are a couple of interesting hyperparameters here: how we define the neighborhood size, or the area around the map, around each best matching unit that's affected by an example, and how we define the learning rate. We define both of these as functions of training time whose value decreases with time. So I hope that code and those concepts are pretty easy to understand at a high level, but it isn't immediately clear how we could implement that code in parallel using Spark, right? So let's look at how we could implement this in parallel by starting to think about what kinds of code features make code difficult to implement in parallel. And things that make programs hard to run in parallel put a hard upper bound on how fast we can make our programs. Amdahl's law, which I mentioned because it's celebrating a 50th birthday this year, shows us that the upper bound on how much overall speed up we can get from parallelizing our programs is a function of the amount of time that our programs spend in code that we can parallelize at all. So if 90% of your execution time is spent in strictly serial code, the theoretical best you could do, even with infinite parallelism and free communication, is a 10% speed up. So it's absolutely worth it to find places where your code is forcing serial execution. So one thing to look out for is algorithms that depend on randomizing their input data. This is a problem for two reasons, one of which we'll see now and one of which we'll see in a minute. The first problem is that shuffling data is expensive, even on a single node. But it's more expensive on a partitioned collection, where reordering in general means sending every element of the collection somewhere else and forcing the rest of the computation to wait for that shuffle to complete. Another problem is algorithms that can only be specified in terms of updating some intermediate state with a single value. If you're a functional programmer, you probably know this kind of technique as a fold. The fold is very useful in serial code, and it's a really elegant way to implement algorithms abstractly. But it can be a problem for parallel code if you only have a way to update a state and not also a way to combine independent states. Put a different way, if you have a reduce operation that takes two things and combines them to produce a third thing of the same kind, then you're probably in good shape. But if you only have a fold operation that takes two things of different kinds and returns a new thing of one of those kinds, then you may have an obstacle to parallel execution. So how can we address these problems? Well, one thing to look at is whether or not we can realize our technique mostly in terms of commutative and associative binary operations. If so, great. The order we run those things in doesn't matter. And the more operations we have that commute, the more parallelism we can expose. And this points to that other problem with having to randomize examples. If your technique really depends on the order you see data in, it's a pretty clear indication that the technique isn't made up of independent operations. Similarly, you might have an online approach that runs pretty well, but if you can replace it with a batch approach and you have some way to reduce the results of intermediate batches, then that may be a way to look at a parallel implementation you can run on Spark. Finally, you might be able to take an off-the-shelf solver or optimizer, like one that Spark has a parallel implementation for even, and specify your technique in terms of that framework. Now, often the serial implementation is really easy, and it takes some outside-the-box thinking to use techniques like these to go to a parallel implementation. But the good news is that for a lot of problems, someone else has already thought about how to apply these techniques. Someone else may have already thought about how to apply each of these techniques to a problem that you're interested in and written it up, whether in a paper or in open source code that you can look at. So when I started implementing self-organizing maps on RDDs, I was able to start with a batch implementation that I'd seen described in the documentation for another library. I didn't even have to look at code. The basic idea behind this batch implementation is that you go through the entire training set for each iteration, record how each example would have affected the map, and then average those together for the whole batch. You then come up with a new candidate map at the end of each iteration, which you use for the next iteration. And the key thing here is that each batch produces a model that can be averaged with other models. In the context of Spark, this means that each partition produces a model that can be merged with other models, and we can have a natural implementation on top of RDDs. Now, this is not always going to be the case for every technique. Not every batch technique is going to be amenable to combining batch results with a commutative and associative binary operation so that you can combine all these partitions together. Even in this case, it's possible to imagine pathological scenarios in which averaging per partition maps can go really wrong. For example, if you have extremely small partition sizes. Fortunately, there are practical techniques usually to address these kinds of cases. And I'm an engineer and not a mathematician, so I saw that things worked, and I didn't lose sleep over it. So let's look at a basic implementation technique for taking batch learning algorithms and turning them into parallel learning algorithms on Spark. Here we're simply looping over an iteration count, and we've delegated most of the heavy lifting of updating our models to a model state class, which holds our intermediate states. The method we're leaning on in the RDD API is aggregate, which does two things for us. It lets us supply a fold operation for the serial part of our program, that is operating on values within a single partition, Aggregate also lets us provide a reduce operation that combines the intermediate states from two separate partitions together. This is a really convenient API pattern that keeps you from getting your hands dirty touching partitions explicitly. The basic template here is a great place to start, but there are a couple of things to look out for. The first concern is that we're referring to a model object within a closure argument. So when Spark executes this part of the aggregate call, it's going to serialize the model object inside the closure and ship that big serialized closure out to each worker. This is inefficient, but it could even cause your program to crash because the default closure size limits were designed to discourage this kind of behavior. A better approach is to use a broadcast variable. So instead of passing the object itself, we broadcast it and pass a lightweight handle to the value in the closure, which we then dereference to get the actual model so that we can use it. This allows Spark to distribute the model more efficiently and for serialized closures to stay smaller. The only difference is that we have to dereference the handle to access the actual value as we see here, and we'll need to remember to remove the old broadcast when we're done with it. The last thing I want to call out in this implementation template is the use of aggregate itself. As we saw, it's an extremely convenient interface for this kind of problem, but it's the wrong implementation. And to see why, let's look at how Spark actually implements aggregate. In a conventional aggregate, the workers perform the fold step on the values in each partition in parallel. But then they send all the intermediate results to the driver, which combines them serially. This increases memory pressure at the driver, and it also makes Gene Amdahl sad because it unnecessarily increases the amount of execution time that we can't speed up by adding parallelism. A better approach is to use the tree aggregate method, which has essentially the same interface, but which performs aggregation at the workers in parallel, combining these intermediate values until you have fewer and fewer partitions, and eventually you have so few partitions that you can send them to the driver and combine those last couple of partitions there. So we've just discussed some general techniques for implementing machine learning algorithms in parallel and some specific techniques for realizing these implementations on RDDs. But I suspect most of the people in here don't prefer to work with RDDs. Am I right? Does anyone really prefer RDDs to other Spark APIs? Thank you. A few of us, yeah. So I'm in the same boat as the few people who raised their hands. I still love RDDs. They're still the low-level foundation of Spark. But I was really excited about RDDs in 2013. It's not 2013 anymore. We should be looking forward, and that means using more modern APIs. And I suspect a lot of people prefer to use data frame and dataset APIs. But before we condemn RDDs and consign them to history, let's talk about the things that are nice about them, right? Since these aspects can present additional challenges as we move to expose our algorithms with more modern APIs. This simple code example illustrates one of the best features of RDDs. Do any of the Scala programmers know why? It won't run at all. Yeah, it's not going to compile. By contrast, this equivalent data frame program will compile, but it will crash at runtime. And I really like type safety because I'm a fallible human, and it keeps me from making stupid mistakes. And Scala's type system, and thus the type safety you get in RDDs, is quite good and imposes relatively little cognitive overhead on the programmer in exchange for a lot of benefits. Another nice thing about RDDs is that you can run essentially unmodified host language code on essentially unmodified serializable host language objects. So in this case, if I wanted to take my self-organizing map model and find where some data that I haven't seen before is going to map in my map, I can just map my RDD to a function that looks up where each example is going to show up in my model and create a pair. If I want to do this in a data frame, even for a relatively simple case, I have to expose it as user-defined function and do some other machinery. So one advantage of RDDs is that they'll execute exactly the code you give them. But this is also a disadvantage of RDDs, that they'll execute exactly the code you give them. What we're doing on this slide is we're generating two large collections of numbers, taking the Cartesian product of these collections, mapping each pair to the result of an expensive function, and then filtering out some of the results. Now, if you don't have a table of prime density handy, the problem with this code is that it's going to generate 10 to the 17th pairs, perform 10 to the 17th expensive operations, and keep only 0.3% of the results. So this is a pathological example, but it illustrates one of the problems with RDDs, which is that it's easy to write pathologically bad code in general. And if you have a query planner, the query planner is smart enough to say, well, hey, if we put that filter before we do the Cartesian product, we're only going to generate the pairs that we're ultimately going to care about anyway. And so Spark's query planner will do this kind of work for you automatically for data frame programs, but not for RDD programs. Another advantage of RDDs is that they'll operate on arbitrary JVM objects, like this 2x2 matrix. Please don't actually declare matrices this way. But to see why this is a disadvantage of RDDs, that they'll operate on arbitrary Java objects, let's look at how this nested collection actually gets stored in the JVM heap. We have an array that contains pointers to two other arrays. So we have 3 objects, each with an object header consisting of a class pointer, various flags, a size field, space for locks. And this outer array is only containing pointers to the inner arrays. So we have 32 bytes of data in our 4 doubles. The actual amount of space that this nested collection is going to take up in memory will depend on how your JVM organizes memory. But in a lot of implementations, we're looking at 8 bytes per pointer and at least 16 bytes per object header, meaning we have 64 bytes of overhead for this really simple matrix. By contrast, data frames use off-heap memory and optimized cache-aware representations to save space and improve performance. So there are a lot of good reasons to go to data frames, even in spite of the trade-offs. You have a simpler interface, improved query execution plans, and better memory performance. But one of the coolest advantages of data frames is interoperability with machine learning pipelines. And the machine learning pipelines API is inspired by scikit-learn, and it allows you to specify entire learning pipelines as sequences of these parameterized components that summarize and transform data. You can then execute these pipelines on data frames, producing values in new data frames, and save the pipelines to disk to use them later. There are 3 key interfaces in the machine learning pipelines library. Estimators take data frames as input and produce transformers as output. Transformers, which include models, take data frames as input and produce data frames as output. And this can be annotating a data frame with predictions from a model or transforming values. Maybe you want to scale them, maybe you want to encode them in some way, maybe you want to hash them. The behavior of both estimators and transformers is controlled by parameters. So parameters can be things like model hyperparameters or simply the names of columns to take values from or write values to. These 3 interfaces fit together in intuitive ways and are simple to use. So let's start to look at how we actually want to put one together. We'll start by putting together parameter definitions. If we put parameter definitions and schema transformers in a Scala trait, which is like a mix-in in other languages, we can reuse code in estimators and in the models they produce. And this is a common pattern in Spark's machine learning library as well. So here we have a trait, which we're extending some classes in MLlib, and we're declaring a single parameter in this example. It's an integer parameter, so we're going to make an instance of this int param class. We're going to provide some user-facing documentation in this constructor so interactive users can learn what a parameter is for. And we're going to supply a validation function so that we can automatically get an exception if the user tries to create a map with a negative width in this case. We want to make sure that the width is at least 1. And then we also provide getters and setters for the parameter. Another cool thing you can do with traits, which we'll see here in an example from Spark's machine learning library, is to make individual traits for parameters that you find yourself using across multiple algorithms. So you only need to define an iterations trait once, or parameter once, if you have a trait for it. You only need to define tolerance or seed or other things you might use across several algorithms once. Now, unfortunately, the particular traits used in this example aren't public interfaces, but it's easy enough to make your own. So the APIs for machine learning pipelines are easy to use as a user and a good place to get started when thinking about your implementation. At the most basic level with an estimator, you need a method to train a model from a data frame. And with the transformer, you need a method to construct a schema for the data you'll be transforming, and a method to actually affect the transformation. So when you're implementing a transformer, the first step is to implement the code that transforms the schema. But this code is also going to show up in the estimator because you're going to be training data on the same kind of data you're going to be predicting on, so you'll need to be able to validate. And if you do validation and transformation in the same method, you can reuse this code. So we're going to put a method like this in the trait that we're sharing between our estimator and our transformer. And basically, we're going to start by requiring that the schema contains the input columns we care about, making sure that the input columns in our schema are of the types that we expect them to be, And then just to keep the user from getting confused, we're going to make sure that the output columns don't already exist in the data frame. This is a matter of taste. And then we're going to make a new schema by making a copy of the old schema with the columns that we're going to add to it for our prediction. In this case, the map entry and the similarity score added to the end of the schema. The training part, which goes in the estimator, can actually be quite simple if you already have a method to train on an RDD. You can just project everything away except the column you care about, convert that to an RDD of vectors, or whatever your training method expects, and then generate a transformer with the model you trained from the code that you have to train on RDDs. So I've elided some details from my actual implementation to keep this example on a slide, but the point is that the actual training component of a machine learning pipeline can be a straightforward wrapper around an RDD-based implementation. And this is not just me taking a shortcut here. This technique is actually used in Spark's machine learning library as well. So I want to close with some practical considerations, things that if you've been developing Spark code for a while, or that if you're new to Spark code, you might not know. And the first one is code like this. How many people in here have written code that looks like this? A few of us, yeah. Yeah, so for those of you who haven't, what this code is doing is it's taking an internal API in Spark, and it's making it public so that you can use it. I'm pretending to be in a package called spark.ml.hacks, although this is going in my project. And then I'm taking a type that's internal to Spark, and I'm making it a public type. If you wrote code for ML pipelines a while ago, like before Spark 2.0, you probably have code that looks like this hanging around somewhere. You may have even written code that looks like this recently. The good news is you can retire this sort of hack, not because the vector user-defined type is a public type now, but because Spark actually contains the same hack now. Spark exposes these types as in a developer API object. So it's not to the level of a public API yet, but it is something you can use and depend on in a library. If you need to define other user-defined types, though, you still need to work against a private API or use datasets and encoders. Another detail you probably want to think about is ensuring that your training data are cached. So here's a good code pattern that's used a lot in Spark's ML library that you can use to cache a dataset or RDD only if it hasn't already been persisted somehow. So we check to see if the data we're looking at had a storage level of none, meaning it hadn't been cached. If it wasn't cached, we'll cache it. We'll do our training. And then, if it wasn't cached, we'll uncache it. So that way, the user gets the collection back with the same persistence state and storage level that they had before. So we've looked at a few ways to improve parallelism, but that doesn't mean you don't have to worry about serial performance. And here are a couple of things to consider that come up in a lot of algorithms. If you're doing a lot of distance or similarity calculations to a bunch of vectors that only change once per training iteration or once per pass through your training set, consider caching the norms of those vectors. Similarly, if you find yourself doing a lot of dot products in a loop, see if you can replace the loop with a matrix vector multiplication. These are just examples of sort of general principles. Right? In general, caching is often a win. Those of us who like RDDs know that caching isn't always a win. And replacing repeated operations with a single simpler operation usually improves performance and readability. But these principles are both special cases of an even more general principle, which is that you can often improve your performance by considering how often you touch external libraries, like your favorite linear algebra library, and how often you interact with them. Because each invocation is probably going to involve converting and copying data so that it can be operated on by optimized native code, and each invocation is going to have a high fixed cost. So you'll always want to double check how well your code performs with small changes, but in general, try and do as much work as possible per library invocation is a good place to start. So today we've covered some things that make algorithms hard to implement in parallel, but we've also talked about some general techniques that you can use to get started on a parallel implementation. Thinking about independent operations and designing an implementation with commutative and associative operations, using batch techniques and combining batches where appropriate, or using a formulation for an existing parallel solver like stochastic gradient descent. We also talked about the nice parts of the RDD API and why you might still want to care about it as a library developer, even if you're targeting newer APIs. We showed how to use the RDD API, the data frame API, and the machine learning pipeline API to support parallel machine learning algorithms on Spark. Developing libraries on top of Spark is an exciting job. You can do really cool things and benefit from a really vibrant ecosystem. And it's really exciting how much easier it's become to do this kind of development on Spark. So there's really never been a better time to get started doing it. Thanks so much for your time this afternoon. This has been a lot of fun. You can reach me on Twitter or GitHub at willbe, or via email at willbe@redhat.com. I may have some Jekyll problems, but I have a blog with topics that includes these kinds of things we've talked about today. And a lot of the work that I've mentioned with the self-organizing map and a lot of other cool things are available on radanalytics.io, which is an open source community I work on with some colleagues. Specifically, the self-organizing map implementation is in a project called Silex. And I'd like to call out my friend and colleague Eric Erlandson has also implemented a cool technique on top of Spark. He'll be talking about that tomorrow at this time, using T-digests for feature importance. So thanks, everyone.
We still have a couple of minutes for questions. Are there any questions?
Hi, I'm just curious, what application do you use self-organizing maps for?
Yeah, that's a good question.
So why you preferred it to autoencoders?
Oh, yeah, sure. So in general, why you'd prefer self-organizing maps to autoencoders. In general, you might not, right? The application I was looking at was high-dimensional infrastructure log data, and I wanted to sort of reduce the dimensionality and find outliers. And the self-organizing map, by sort of tracking the distribution of similarities to the best matching unit, was a useful way to find outliers in a lot of unstructured log data. I gave a talk about that at Spark Summit last summer, actually. I could send you a link if we talk about it offline.
Hi, another question from me. So on one hand, you were talking about RDDs and the type safety. On the other hand, you were talking about data frames and optimizations. Was there any reason you haven't mentioned data sets, which sort of combine those two things together in the new Spark?
Yeah. So data sets is an interesting area because you have a lot of static type safety. You still have that lack of safety at the encoder boundary. But I think, yeah, absolutely. As I mentioned, if you're doing stuff with a lot of user-defined types on data frames, you should probably be looking at data sets instead and defining your own encoders rather than trying to define your own user-defined types. Data sets really do get you the best of both worlds in that case.
Okay, any more questions? No, in this case, let's award the speaker with a round of applause. Thank you.
Okay.